Hello and welcome to In Simple Terms with Satish. Today we are talking about how online games keep everyone in sync. Let us start with the technology first. Online games keep many players feeling like they are in the same world, even though every controller input, shot, jump, and movement update is traveling across imperfect networks. At first, it can sound like one clever feature, but the real story is a system of sensors, models, rules, feedback loops, and trade-offs that has to work in the real world, not only in a demo. Let us understand this with a simple everyday example. Imagine several friends trying to act in the same movie scene while hearing each other with a small delay. If everyone waits for every line to arrive, the scene feels slow. If everyone guesses too much, people talk over each other. A good online game does both. It predicts locally so the player feels instant response, then checks with the server so the shared world stays fair. Now return to the actual technical concept. Under the hood, the stack has several parts. First, client prediction, where your device shows your movement immediately instead of waiting for the server. Second, server authority, where one trusted system decides the official game state. Third, interpolation, where other players move smoothly between delayed updates. Fourth, lag compensation, where the server accounts for network delay when judging fast actions. Fifth, rollback, where the game rewinds and corrects state if late inputs prove the prediction wrong. Sixth, anti-cheat and validation, where the server rejects impossible movement or suspicious actions. That list matters because modern technology is rarely one model or one app screen. It is usually a chain. Data has to be captured, interpreted, checked, acted on, and corrected when reality disagrees. For engineers, the useful idea is this. The practical pattern is authoritative state with local illusion. Make the player feel instant, but let the server remain the referee. The catch is that every trick has a trade-off. More prediction feels fast, but can create corrections. More server authority improves fairness, but can feel delayed. Higher tick rates give more precision, but cost more bandwidth and compute. This is why the topic matters for students and builders. The visible product may look simple, but the engineering work is in the hidden boundary conditions. What happens when the input is noisy? What happens when the user behaves unexpectedly? What happens when the system is confident but wrong? What gets logged, reviewed, updated, and rolled back? A good way to learn the topic is to sketch the pipeline. Draw the input signals on the left, the decision or prediction layer in the middle, the user-facing action on the right, and the failure modes underneath. That one diagram will teach more than memorizing the buzzword. The clear takeaway is this. Online games are latency hiding machines. They do not remove network delay. They design around it with prediction, interpolation, rollback, authority, and careful validation. In simple terms, the magic is not the label. The magic is the system design underneath and the discipline to know where the system works, where it fails, and how humans stay in the loop. If this helped you understand the topic in simple terms, follow or subscribe to In Simple Terms with Satish. I will see you in the next episode. A useful way to test your understanding is to ask what the system knows directly and what it only guesses. The gap between measurement and inference is where many failures hide. Another useful question is who owns the decision when something goes wrong? The model, the sensor, the operator, the policy, or the product design behind multiplayer game networking and netcode. That is why good engineering explanations should include the happy path and the messy path. The messy path is usually where the real architecture becomes visible. For students, this is the habit to build early. Do not only ask what the technology does. Ask what evidence it uses, what assumptions it makes, and what happens when those assumptions break.